waxing, and it's prone to errors. And the challenge is that in order to interpret these images, the radiologist have to have a lot of expertise, due to which, depending on the radiologist, the accuracy of the diagnosis changes. So that is one of the main drawback with manual interpretation. And it's also that countries like India, we lack enough radiologists. We have only one radiologist for 100,000 population. I'm talking about general radiologists. And now if you're talking about specific radiologists in MRI and these things, we have very few. So how do we address this issue? So that's where artificial intelligence can come into play. So just to cover the basics, because I was told that there are people who might not be knowing the basic definition. So I'm just covering the definitions here. So AI is a field that involves in development of computer algorithms which can perform intelligent tasks. So these intelligent tasks can be a simple hard-coded rule. You can say that just trigger an alarm at this time, right? So it could be as simple as that. It can be a sophisticated system, like I think you all might have used ChatGPTs, right? So it can understand the task, and it can understand the inputs. So that is artificial intelligence. Now, what is machine learning? It's a branch within artificial intelligence where we deal with computer algorithms which have capability to learn without being explicitly programmed. What it means is that we have some kind of training data where we look at the data and understand the patterns, and given a new input, we try to infer from it. So deep learning is a branch within machine learning, which is inspired by how our human nervous system is connected with millions of neurons. So we have the input and output layer connected with different mathematical approximations of neurons, and then we try to understand the relationship between input and output. So the AI has been used in healthcare over the last 2 decades, but in the last 5 to 7 years, it's been very well used in different healthcare applications. Initially, we started AI as a tool to optimize the efficiency. Like, for example, you want to digitize the records, so we have AI algorithms to do OCR on top of these reports and digitize it. But over the last 5 to 7 years, we are seeing a trend where AI has been instrumental in not only the operational efficiency, but in patient care as well, starting from disease diagnosis. So by looking at an image, can we tell whether the person is having cancer or whether the person is having an abnormality? It's being used in where we can whether the patient is responding to a chemotherapy. And COVID-19, we all have seen how different companies use artificial intelligence to speed up the drug discovery. So we have a lot of digitized health records, which contains vital information about patients and medical history. So again, AI has been instrumental in taking these EHRs and actively predicting any kind of risk assessments or coming up with what could be the potential illness that we can recommend the user for continuing. So AI has been instrumental in different departments. As we discussed, it's been vital. It's been playing a vital role in disease diagnosis, treatment monitoring, where now we are able to know whether the treatment is working or not. It has been instrumental in drug discovery, and how electronic health records we are leveraging the information and then coming up with screening regimes that we can recommend to the individuals. So robotic surgery is one area which we are seeing a lot of advancements in the recent years with the advancements in both robotics and artificial intelligence. So now we are able to do precise surgery, and we can do it remotely as well. Telemedicine is another area again where we are seeing a lot of use of AIs in terms of generating automated prescriptions to assist radiologists in triaging the patients or even um, giving a personalized, giving an automated report generation for the doctor. Think again how a temperature is changing over time, right? It's important that the frames are registered. So there we have a registration algorithms in order to register the frames in a series of images. The fourth problem which we see is a reconstruction. So we will be collecting different slices of images and we might want to reconstruct the 3D slice. And the medical imaging equipment has a lot of noise. So we might want to reconstruct a denoisy image. So these are the four problem statements that we see mainly in medical imaging. But uh, but recently we are seeing other use cases also. These are not so prominent, but we are seeing mainly in terms of image synthesis. Now we want to generate images or generate medical images, which could help the doctors. So you can treat it's not only just that the data synthesis which we are doing. It's not just to improve the machine learning algorithms. We can see this as a use case for the doctors to train them. So what happens is in many of the medical imaging, we often see a variety of diseases, but their incidences are very low. And if you're training a radiologist, so if you're talking about different cancers that are there are hundreds of varieties of cancers that we see. And specifically in breast cancer, we have tubular carcinoma or papillomas, where the incidence are very low. So in order to train a radiologist for these diseases, it might, we might not be having every time a good number of cases to train the radiologist. So that's where image synthesis can also play a role. So as we discussed, it can also be used for treatment monitoring, where you can collect a PET CT scans and you want to know whether it is working or not, or how, whether you want to reduce the dosage of treatment. To understand that, it's also one area of treatment modeling. So report generation by combining with multimodality is also another area which we are seeing in terms of medical imaging. Now, these are the main problem statements. So let's understand what is the typical journey that happens in developing and deploying a healthcare solution into clinical practice. So the first and foremost step is to identify a problem statement with a true clinical need. So though this looks very trivial, but it is a crucial aspect because not all problem statements might have true clinical need. So in order to understand whether the problem that you want to work on is having a true clinical need, we have to study the challenges with existing technology. What is existing technology, and the technology that you are proposing, is it having more risks versus more benefits, right? We need to do that trade-off. This is important to do in the beginning itself because any kind of healthcare product which we develop, it has to go through regulatory process. And the regulator is going to check what are the risks and benefits of the proposed technology. And if they see a lot of risk, then it might not be clear to be used in the clinical practice. Since medical in healthcare technology, any kind of development is time consuming and money taking. It's important you plan this in the beginning itself to understand what the risks and benefits of the technology. And once you're clear that okay, I want to start on this problem statement, the next step for any kind of AI use case is getting as much as data as possible. And it's important for medical imaging, we pool as much as data as possible because many of the diseases, they are dependent on demographics, they're dependent on the populations, they might be dependent on the age groups as well. So getting as much as data from many sources is important in both in terms of variety and as well as in volume. So if you talk about any kind of labeling of an image, right? For example, if you want to have a image and you want to classify objects, so we can always use human readers and then we can label them. And the chance of error would be very low. But if you're talking about labeling the medical images, we need to understand that even an expert radiologist accuracy could be as low as 90 to 95%. Now, if it's a junior radiologist that's being annotated, the accuracy could be as low as some 60 to 70%. So, and data annotation is very important because garbage in is garbage out. If the labels are wrong, whatever model we are training might not perform well in the real scenarios. So this is very important because I have seen in many scenarios where we use or where we trust the ground truth that is there already in the open source data set. So we will be taking some open source data set and we will just assume that the label is correct. But it's important that we question the labels, how the open source data set or any kind of data set, how we are labeling. Because annotation by a single radiologist is not sufficient. And even if you're annotating a single radiologist, then is it, what is the experience of the radiologist, right? Because that varies the accuracy of the prediction. Very often, we typically take the majority voting, like if you have, we pass the images through multiple radiologists and we take a majority voting. That's a common strategy that we use. So the other way of doing this would be having a follow-up data. So if you're talking about cancer, medical image data is not always accurate. So you'll be taking the histopathology data. And then anticipate the potential biases that you might foresee. It could be imbalance in data because you would end up having a lot of negative samples compared to positive samples. And when you get this clinical data, right, often there might be biases in terms of inclusion. So for example, you are collecting the data of, for example, you're collecting the data of old population, right? For example, you're talking about cancer and you're assuming that the risk would be higher in age greater than 45 years. So that could be an inclusion criteria. So if you're taking that kind of data and you're applying it on population whose age is less than 45, you might see poor performance. And data source is another common error that we might foresee. So I can give you a small example where a research lab has trained a model, they got the data, and they have a single center data. So they trained the model with the data that they had, and they got very good results, and they were excited. So they wanted to test it with other hospital data, and it performed very poorly. When they went back and understood what could be the potential reason for it, is that it is because whenever there is a lesion that the doctor is finding, they're marking some markers on the images. And due to which the model, instead of predicting whether it's abnormal or not, it is just predicting whether it's X mark or not. So it could be these kind of data source errors we might see. So it's important that we look at the data and understand what kind of data source errors which we might foresee. So once we have this, until this, it is whatever the data steps which we are talking about, curation steps, this is common for any kind of AI problem. And once we have this, we can take any kind of off-the-shelf models, or we can take any kind of custom model and develop the model. But it's important that we evaluate on independent test data sets in order to understand the accuracy of the models. Explainability and interpretability are key to clinical integrations. So especially when you're talking about deep learning algorithms, right? If you just give whether this image is positive or not, it is not sufficient for the doctor, because doctor has to give this diagnosis to the patient. So it's important that the doctor understands why the model is saying whether it's yes or no. So taking this step, taking care of this step in the beginning is very crucial. So make sure you can make your models explainable. We can use maybe some kind of class activation maps or some kind of radiomic features one can use in order to make the models more explainable and interpretable. So make the models more generalizable and utilize appropriate performance metrics because some use case demand some metrics, like if you're talking about the general screening, maybe sensitivity and specificity might be more appropriate metrics, and estimate where the model works and where it doesn't work. This is very crucial step. It's not always that whenever we're developing AI solution, it will work for all the use cases. Like if you're talking about mammography images, X-ray images for predicting the breast cancer, it's not that uh, we can say that it will detect any kind of breast cancer. We can always come up with claims. Maybe it will detect only in the symptomatic population where the patient is already having some kind of symptoms. So if you could understand it, it is easy to pass the next step, which is clinical trial and regulatory. Any model that one develops in healthcare, it has to go through clinical trial and regulatory process, which involves typically taking the developed AI solution, deploying it in a hospital, and understand whether it's performing well or not by doing prospective studies. And while doing so, we will be having clinical objectives that what is that we're claiming? Are we claiming that we will detect cancers in all women, or are we claiming that we'll be detecting in a subset of population? This is important because once we pass that, then only we'll get a clearance to deploy in healthcare settings. So once that is done, the next step is to understand with doctors, right? It's not done like just because one get a regulatory clearance, the job is not done. We have to work with doctors on how to improve the clinical adaptability, continuous monitoring of the model to check for accuracy changes, and retrain with new data whenever it's required. You get more data, we can understand how the model is performing and retrain. So I just want to cover a case study to explain the implication of the post-market surveillance, which is like the last step which we discussed. During COVID-19, Niramai, where I work, along with ISC and Harvard, we have released this AI system called XSATO. Because during COVID-19, RT-PCR in rural areas, it used to take 5 to 7 days to get the report. And by then, the severity of the patient used to increase. So to address this issue, we wanted to use the X-ray images. The Italian Radiological Society has told that we can use X-rays also in order to know whether whether the person is having the COVID-19 or not. So what we have done was we quickly got data. We had developed this complex framework of multitask learning because the data of COVID-19 is very less. So we want to leverage the other information that is there. That is, we have close to 1 million images of chest X-rays for different abnormalities. So we created this shared network where we try to train this network for multiple tasks. And we created the network and we are able to get very good results. So we quickly released this WhatsApp application where the doctor can send the image and we will be generating a report with probable locations of the abnormalities, not only just COVID-19, but 14 other lung abnormalities. Also, it categorizes. So, but once we release this, some of the doctors said that some of the doctors said that it was not working. So when we looked at the data, right? So we have understood that we are seeing some doctors wants to test the images, test the application. So they're just sending some traffic images or some natural images which they're sending. And since we don't have any filter, it is predicting some kind of classification because For the deep learning, whatever the image it is, it still process and then gives some kind of prediction. So we are generating a report even for these images. And we have seen that some of the images, though these are like genuine X-ray images, we saw that it was not taken properly, or it requires cropping because there is a lot of background region. So once we learned that, right, we designed a new pipeline to help addressing this issue. So what we have done was, so we created this pipeline. The first task is, first we want to verify whether it is X-ray or not. So if it is not an X-ray, we just want to send a message to the user saying that it's not an X-ray image. And if it is an X-ray image, it passed to a second step, which tells whether it is a good or a bad image. So we can treat this as an image quality check, because as we discussed, if the input is not good, the results are not reliable. So we have a good bad X-ray classifier, which basically tells whether it's of a good X-ray image, which we can process or not. So whenever if it is bad also, um, we had designed a captioning network which tells why this image is bad. Is it because of the lighting issue, or is it because of some kind of angle? So we have that custom image captioning network, which basically communicates to the user saying that take a image with these guidelines. So once, even if it is good, then the next step is we want to crop the portion of the image which is really required for the inference. So, and we also combine this manual technician so that the inference what we do is more accurate. So that was the so that's what we have seen in this case study. It's important that if you know why the model is predicting and how the model is predicting, we can always design strategies to improve our accuracies. So this is a hypothetical example which I want to walk you over so that you would understand some of the common mistakes while developing a AI system in the healthcare. So think about a researcher A who wants to classify pneumonia using a PET-CT image. So what the researcher has done is they downloaded the open source dataset. So the open source dataset consists of 100,000 images of 1,000 persons obtained during COVID-19. And the labels are annotated by a single radiologist. It could be a junior radiologist or any radiologist. The information is not available. So what the researcher has done is they have simply taken 80-20 split and then trained VGG16 network. They got like 90, the researcher got 99% accuracy on the validation set. He's very happy. So directly deployed in a real setting. And once it's deployed, it didn't perform well at all. So just to make it more interactive, maybe can the audience type what could be the pitfalls for this approach? You can message in the group or maybe unmute and then um, mention what could be the potential pitfalls with the kind of approach. Maybe I'll go back to this slide. If anyone thinks that in this approach there are some pitfalls that you see which the researcher should take care of, you can message in the group. I will read it out. It's not tested on real-time data, which is a very good answer, because what the researcher has done is they have taken a cross validation. Like it's like a cross validation where you have taken 80% and 20%, but we haven't tried anything in the real time and we deployed it. So that's a very good answer. Any other comments from the attendees? Random split, yes, that's a very good suggestion again, because we are talking about one split. Maybe it could be such that that split is having high accuracy.
Hello. May I interrupt
Yes.
you, Dr. Shiva? I have a query. I have a query.
Yes.
May I interrupt you?
Yes, sure. Yes.
Okay, thank you. Actually, I am working as an assistant professor and also pursuing my PhD from the same institute.
Okay.
And my research topic is prediction of lung disease. Like
Okay.
I have started my PhD time of COVID, so I have chose this topic. And I'm not using image data set. Actually, I'm using textual data set for that.
Okay.
And I'm facing the problem like the I have trained my model. Like the model is ensemble model, ensemble voting, which in which I have combined multiple classification technique. But I'm getting the problem that my model is giving 100% accuracy. I
Okay.
have trained it many times, but on the data set I got from UCI repository and all of that, but I am getting 100% accuracy. And at time of progress report when I was presenting, then the question raised, then how your model can give 100% accuracy?
Right.
It's the issue in of me. How can I reduce the accuracy of that model? Actually,
So
that is the issue.
maybe yes. I think we can discuss this offline also because in this setting also, whatever we are doing, we will be getting 100% accuracies. Whatever example I have mentioned, this happened with many times. What happens is that maybe I'll cover the pitfalls. Maybe you would be able to relate to some of the pitfalls with general approaches, and then maybe we can take it towards the end of the session. This one. Does that sound good?
In the end of the session, you are saying,
Yes, because I want to walk over this example which covers
okay,
different pitfalls, and then we can discuss
oh,
after that.
okay, sure. Thank
Okay.
you.
So direct deployment without pre-processing of images may create issue. Yes, some kind of pre-processing also might be important. Any other suggestions? Okay, maybe let me walk over. So, so there's a data leakage. I'm not sure if you have observed it. So what has happened here in this data set is the researcher used 100,000 images. However, it is from 1,000 persons only. So which means for each person, we are almost having 100 images. So what if the same set of images are in training set and you are doing it in the validation set? So the researcher might be able to get 100% accuracy because there's a data leakage that is happening here. Didn't check ground truth veracity at all. So the researcher has trusted the labels that are given in the open source data set. But what if it is a single radiologist? So how the researcher can overcome this issue is we can take these images, maybe consult with some 2 to 3 radiologists, take a majority voting of the radiologist output, and then train the model. That would help. And regarding the training data leakage, whenever we do this kind of data set that we have, uh, one of the things we should ensure is that the training and testing, there is no data leakage. Whenever we do this, we can ensure that whatever images of a person is there in the training set, the image, the remaining images are also in the training set, but not in the validation or test set. So that the researcher has to ensure. Potential biases, because this was collected during COVID-19. So that point of time, we are talking about pneumonia. So the entire labels could be about COVID-19 pneumonia rather than a general pneumonia, right? So that's also one reason why when we directly deploy a real setting, it might still be predicting a different pneumonia pattern and it's not working on the general pneumonia population. Data source could be an issue because maybe the entire data was done with one set of medical device, and when we went with other medical data device, like we're talking about other company PET CT, maybe there are changes in the in the information that is there in the metadata that could also might result in some kind of low performance. I think Professor Katke mentioned, I think some kind of pre-processing. During those scenarios, we can employ some kind of segmentation of the foreground and then give those images so that not any kind of metadata that we see that can be removed from the data. And we said that the researcher is getting 99% accuracy, but the challenge is that accuracy might always not be a reliable metric because if you're talking about pneumonia, there might be only 10 cases in these images in this data set with pneumonia. So if you just go with accuracy as a metric, even though you classify everyone as positive or everyone is negative, you would end up having 99% accuracy. So, one should look for sensitivities and specificities or AUC metrics for that. Lack of independent testing, which we have briefly described. And the fundamental problem is the researcher didn't look for risk-benefit analysis. We're talking about pneumonia detection with PET-CT, which is a nuclear imaging where you inject radioactive isotopes to understand whether it's a pneumonia or not. So the question is, X-ray imaging has already been there, which is less costly, less invasive, then is it worth, right? So that is one key factor the researcher has to consider. So I think Professor Poonam, you mentioned about high accuracies because in order to understand, we should look at all these kind of data sources that some of the errors which might happen with the data set. So I might not be able to directly comment on it, but we can discuss offline to understand what is your data sets, right? How you're getting the accuracies, understand any kind of potential biases. Then we would be able to comment more on that. Okay, so with this, I'll move on to the next topic, which is where I talk about thermal imaging. So whatever we have seen, those are the standard imaging modalities. Thermal imaging is something that is coming recently in the last decade, though it has been in existence since long because of the advancements in thermal hardware and artificial intelligence. We are seeing a lot of applications with thermal imaging. So what is the need for thermal imaging? We already have X-rays and other imaging modalities. What is the benefit that we are seeing with thermal imaging is that it is of low cost. If you're talking about countries like India and we want to provide healthcare access to even the remote areas, we want healthcare imaging technologies which are of very low cost and which are very portable so that we can give it to hospitals and hospital can take this outside and conduct camps. It should be radiation free so that it doesn't harm the patient. Non-contact is beneficial so that we can automate the imaging at the same time, make it a comfortable experience for the person. And thermal imaging, we are also seeing contact-based thermal imaging, where we have wearable devices which you can connect. For example, there's a wearable patch which you can keep it on the skin and it will regularly monitor the temperature as well. And for the breast cancer, we have wearable bra, which tracks the heat patterns, and then whenever it sees any kind of abnormal heat patterns, it could trigger an alarm. Home monitoring is also one potential application of thermal imaging, where because of its low cost, we can use it at home and we can monitor the patients as well. So what is thermal imaging? So it is nothing but measure of surface temperature distribution. Every body emits naturally long-wave radiation, which we can use thermal cameras to capture it, and we will convert it into an image format as you are seeing. So each pixel here represents some temperature value, like 35.5 degrees centigrade or 34 degrees centigrade. So how is it done? So let's say you have a target object and there is a thermal camera. what happens is this thermal camera measures three different energies that might come from. One is the energy that is being emitted by the target object. One is that's being reflected by the target object from the surroundings, and one is the atmospheric energy. So once we get this energy, we can do the thermodynamic modeling, and we will be able to get the temperature of the object. So I'm walking over you this because if you're using thermal imaging, one need to know some of the parameters if you want to get the accurate temperature values. As you can see, the thermal cameras approximate the temperature using this equation. And this equation has five parameters. So Boltzmann constant is a constant parameter, which we don't have to worry about. But emissivity changes the temperature values that we measure. So if you're measuring for a human body, you can set it to 0.98. And if you are doing for other applications, we can change this emissivity to get the accurate temperature values. So reflected temperature is something which gets affected. So how we avoid it in medical imaging is that we ensure that there are no heat sources when we do the imaging. So that way, this parameter is more or less equal to the surrounding temperature, ambient temperature, which is around 20 to 25 degrees centigrade. Atmospheric transmissivity, since we're talking about air, it's close to 1, because of which anyway the atmospheric temperature might not play much role. So what this thermal imaging is measuring is raw temperature values. So how does a doctor interpret it? So what we do is we take these temperature values and convert it into color palettes. So as you can see here, this image has a minimum temperature of 20.9 and maximum temperature is 31.8. So what the cameras do is that they will assign this 20.9 to black and 31.8 to white. And whatever temperatures are in between, they will linearly assign the temperatures to colors. And then you'll be able to see these kind of images. So this is a rainbow color palette, which is very commonly used in medical thermography. And the next two color palettes, which you're seeing, grayscale and inverted grayscale, these are also common color palettes, which is very good if you want to analyze the vascular activities. So in this image, you don't see much of vascularity, but you would see regional activities. Whereas in these images, you are seeing the vascular structures which you're seeing on the neck. This iron hot palette is also something which is being used, but it's mainly used for industrial applications. So if you see the applications of thermal imaging, breast cancer is like the prominent is a prominent use case of thermal imaging. I'll walk you over in detail about how thermal imaging can detect breast cancer and why is a breast cancer. But if you are interested in some kind of applications you want to try, I'm also keeping the open source data set that's available and what are the potential problem statements on the right hand side. So diabetic foot ulcer is a serious complication among the patients who are suffering with diabetes. What happens is people who are having diabetes, they're prone to diabetic foot ulcers, which might lead to foot amputation. So this is as high as 20% of whom diabetic foot ulcers are seen. So it's important that if it is caught in the early stages, it could be simple surgery in removing it and giving a medication. But if you leave it for long, it might lead to amputating the entire feet region or half the leg region, which we're seeing a lot of cases these days. So what happens whenever there's a foot ulcers or whenever the nerves dies, we don't see any heat pattern or we see a lot of heat pattern, right? Which means we see a cold area or we see a hot areas. So by looking at these thermal patterns, we have a lot of research that supports that thermal imaging can detect diabetic foot ulcers in their initial stages. And the advantage, as we discussed, it can be as simple as an image of food, and we would be able to tell whether the patient have any kind of diabetic foot ulcer or not. And just to understand what is the current standard for diabetic foot, if you see, um, there is no direct standard, but people use needle pricking, where they try to use needle to prick different uh, points in the feet, and they know whether they're feeling pain or not. So thermal imaging could be a quantified way of giving a view to the doctor. Onchocerciasis, which is a leading cause of blindness in African and South American countries. What happens is there is a onchocerca worm which can transmit from one person to other person through black fly. This parasitic worm um, can reproduce itself in human body, and it can grow up to 15 to 45 centimeters in the body. And the female Onchocerca volvus lays thousands of eggs per day. So due to which whoever is infected with this disease, they will see a lot of skin allergies, and these worms can traverse to the entire body, and it can reach eyes and leads to the blindness as well. It's a very prominent disease in African and South American countries. And the only way to identify this is taking a skin sample and then understanding. But we're talking about African, South American countries where the healthcare infrastructure is not that great. So, in African, there's only one or two labs that could interpret these images. So, thermal imaging has been vital again here. It has been found that thermal imaging can detect these onchocerciasis worms because they require more blood and they're close to surface, due to which they radiate more heat, so they generate more heat. And thermal cameras, which can measure minute variations up to 0.05 degrees centigrade, we would be able to capture these variations, and AI can be used in order to identify where the nodules are and whether the nodule is an onchocerca volvus or not. So again, if you're talking about surface imaging, right, neck has different different vessels that connect the brain and heart as well. So any kind of vascular disorders you want to study in the head and neck, thermal imaging could play a good role because these vascular structures are close to surface, and thermal imaging can detect these variations. So apart from it, it's been found to be used in identifying whether there is a thyroid cancer or not, or also whether there's oral cancer or not. There's a database from Visual Lab which open sourced different images, different patients' images of thyroid images with labels as whether the patient has any kind of thyroid cancer or not. I think one trivial application is any kind of injuries, because if there is an injury, there is an inflammation which leads to high heat pattern, which can be captured with thermal images. So any kind of muscle tissue strain, or any kind of sports injury, or deep vein thrombosis, all these are very good use cases of thermal imaging. And other use case could involve, I think, during COVID-19, we all have seen this automated fever screening where we can identify from the images automatically the temperature of the person walking in, and then we'll be able to screen whether they're having high fever or not. And the other way of doing COVID-19 at that point of time is also getting the respiratory rate, because just fever screening alone might not be, though it might have high sensitivity, it might give a lot of false positives. So the second way of filtering these people was to identify the respiration rate. If they're feeling, if there is an abnormality in the respiratory pattern, that's a second alarm, to categorize the COVID-19 patients. So respiratory rate estimation can also be done with thermal imaging. And again, with this respiratory estimation, we can even measure what is the amount of stress, or also, there is a research that talks about how we can quantify the stress based on the thermal imaging as well. Apart from it, veterinary medicine, unlike humans, animals can't express their pain. So veterinary medicine is has been using thermal imaging in order to identify the potential locations of where the pain is, and even in, I think, human also, in order to understand where the pain is, thermal imaging has been crucial. Apart from it, treatment monitoring is one area where we take series of images over the treatment, and we see whether the treatment is working or not. It could be a simple pain treatment itself, where you are giving some medication or you are doing some kind of massaging at that location, and you want to know whether that pain is going away or not. So thermal is a good way to quantifiably capture that variation. So with this, I'll move on to the next the final topic, which would be how we can combine artificial intelligence and thermal imaging to improve cancer detection. So the first question is, why breast cancer, right? So yes, sorry, any question? Or maybe before moving this topic, if there is any questions, I'd be happy to answer and move on to this topic. Are there any questions?
Please raise the hand if you have any question.
Yeah, I do have. Is it okay? Can I?
Yes, please go ahead.
Okay. So the previous one,
yeah.
Okay, you shown one diagram, right, where it contains complete workflow of a application.
Right.
Okay. So the first thing actually, like how it is like being verified and validated actually. Yeah. Sorry. Then we have to move forward actually. 13 or 14 slide. The block diagram.
Yeah, this one.
So next one, sorry, next one. So there is a block diagram, right? One, yeah, okay. So so usually, generally, this kind of applications actually. So to reach to deployment stage, usually, what are the various verification and validation strategies being followed? That is my first clarification. Second one, usually, how long it will take to get mature actually?
Okay, I think very good questions. So typically, what happens in any kind of machine learning life cycle is in a clinical is we have something called as lab testing, where we just do some kind of cross validation to understand. Then the next aspect would be validating on an independent test set. It could be the open source data sets that are available online, or just partnering with some hospital and then get the data set and validate. But these are only the two steps to check whether the results are good or not. But before deploying to the hospital, one should do a clinical study, which is most often the prospective analysis. What happens here is you have developed some model, and without any training or anything, right? You take this model and then you will deploy in a hospital, and you don't have any control on the model performance now. And the hospital would be verifying what is the clinical performance. So that's what is the clinical objective. So let's say you have developed a model for lung cancer, and then you are saying that you are getting 80% accuracy for identifying whether it's a cancer or not. So you will be articulating the claim as a clinical objective and doing a prospective study where you give this model, and the hospital will be blindly testing the performance. And during this period, you don't have any control to change the weights of the model or change any kind of even the pre-processing also you will not be able to do once the model is deployed, once the model is sent for verification. So these are the three different steps that happens. One is the lab testing, where you will verify. The second one, it goes through the retrospective testing we call, where either through independent tests or with the available data sets, we validate. Then it goes for a prospective testing, where we just give it to a third party and then we will ask them to test. Once you get good results, then you'll go for a regulatory clearance. And then you can go to the hospital for commercial deployments. So these are the 4 steps that you see.
Yeah. Okay. Sorry, actually, like once again, usually these steps, actually, what were important steps you mentioned, actually, right from lab testing to field testing or clinical testing. Okay. So, what is the
Right.
time frame? Is it we can say 1 year time frame?
Oh, it varies a lot because I will tell you, even to get retrospective data from a hospital, right? I'm not even talking about prospective study. I'm talking about retrospective analysis also. To get the data, one need to get an ethical committee clearance. And it depends on the hospitals which you are partnering with. Because sometimes these ethics committee meetings might happen once in 6 months.
Okay.
So once you get this ethics committee clearance, then then they will allow you to collect the data or to get the data. So again, to get the data, it might take time as well. And sometimes, depending on the problem, the time also varies. If you're trying, there are use cases where you have to monitor the patient for 3-4 years, right? In
Okay.
those
Okay.
scenarios, you
Got it.
might have more time. But otherwise, in order to take a solution and then you want to deploy it, I think I would say the best case would be 1 year at least.
Okay. Okay.
That's the best case because one, you have to first develop the model, do a retrospective analysis, and then for the prospective analysis, you are testing the population, right? So then there is a concept of how many cases you'll be testing. We can't arbitrarily test some 100 subjects. There should be a sample size justification. So that depends on how many positive incidences that are happening. So now, let's say you said that you want to collect 1,000 participants, then it depends on the footfall at the hospitals. But assuming the best case, I have seen startups that were able to come up with some kind of deployment in 1 year. But for some startups, it might, for some companies which I have seen, it might take 3 to 5 years as well.
Okay. Okay.
In our experience, in some other clinical studies, we took 2 years also, 2 to 3 years to complete the prospective clinical study.
Thank you.
Any other question? I think Mr. Utpal, any question, Mr. Utpal?
Yes. Hello.
Hi, yeah.
Hi. I don't have any questions. Sorry.
Okay.
In common color palettes for visualization slide, the grayscale.
Yeah.
So, is it possible to maybe through imaging? Is it possible to measure jugular venous pressure, that movement of that, the pulsation actually?
We might be able to. I can't concretely say, but the current thermal cameras can measure variations of 0.05 degrees centigrade. So if you're talking about a time series data, when there is a change in the blood flow, we have seen changes in the temperature values. So maybe there is no concrete research, but studying this temperature change might help in understanding the pressure or any kind of flow aspects as well.
Okay, so you mean to say when there is a change in the flow or pressure flow, then it will reflect in a image and thermal image, and obviously we can to some extent calculate actually like pressure. Right? Is it something like that you were trying to say?
Yes, right.
Okay, okay. Thank you.
Yeah. So because from the face thermal images, we have seen people estimating the respiration rate, people estimating the heart rate by looking at the variations in the temperatures at the nose region. And we have also seen people claiming that we can detect thermal cardiovascular disease by looking at the face and hand temperatures. Because what happens is that if the heart is not pumping well, you might see asymmetry in the heat patterns. So they measure the temperature at the eye regions and then try to compare the symmetry. They measure the temperatures at the hand regions, try to measure the asymmetry. So any kind of asymmetrical heat pattern would be because of the inability of the heart to supply it, symmetrically to the both the body parts. So that's an indicator of cardiovascular diseases.
Okay. Okay.
So that's the
thank you.
claim. Again, all of these. So as I briefly mentioning, thermal imaging has been there since long, but only in the last decade we are seeing its clinical applications. Very well. Like even if you see the PubMed research that is there,
કોનો ફોટો કે છે અંકલ
Dr.
દેખાય છે
Krishna.
કયા અંકલ દેખાય ક્રિયાંશ ને
Krishna ma'am, please mute yourself.
Okay. So even if you see the latest research, only in the recent years we are seeing a increased spike in the research that's happening in the thermal imaging. So all of these use cases which we're discussing are like very initial stages, and definitely maybe in the next decade we see a concrete use of thermal imaging in a clinical application.
Okay. Okay. Thank you.
Yes. So yeah, now I'll be talking about how AI has been changing the way we're detecting the breast cancer. But before going to what is the use of AI and thermal imaging in breast cancer, but why breast cancer? Why not any other cancer, right? So breast cancer is one of the leading causes of cancer deaths among women all over the world. If you see the statistics in 2020 alone, more than 684,000 women lost their lives to this disease. The incidence is also very high. In almost all the countries, it has the highest incidence. And in also majority of the countries, it is the leading cause of deaths as well. So countries like US, though the incidence is high, the survival rate is also around 80% because they have these systematic screening programs, they were able to do it. But developing countries like India, every alternate woman diagnosed with breast cancer are losing lives. When we looked at what are the potential costs for it, we found some gaps. Just to tell you, right? So breast cancer is one of the most curable cancers if we detected in the early stages. If we detect the tumor size is less than 1 centimeter, it could be simple surgery and the 5-year survival rate is as close as 100%. So it is one of the most curable cancers, but in our country, we are losing every alternate woman diagnosed with breast cancer. So the main gaps in the current techniques is that whatever works in Western world of US or Europe, we are not able to completely implement it in India. X-ray mammography, which is nothing but the X-rays to identify the density differences. So what happens is we pass X-rays and if there is a high tissue density, it absorbs more, and low tissue or fatty tissue, it transmits the X-rays.
Siddhartha Ralada. Madhuri. Siddhartha కూడా అడిగాడే.
Hi, Dr. Kumar. Can you
Siddhartha లింక్ అడిగాడు.
In breast cancer, you can read these publications. Yeah. Thank you, and I'm open for any kind of collaborations as well. If anyone is interested in working on thermal imaging with AI, wonderful to collaborate and work on more projects. I'm happy to take any questions.
Hi, thanks for the session. And one thing actually, like, when we compare with the regular reports versus whatever product you have shown, AI-based product report, how it is different actually, like, whether it contains some kind of indication like this report is recommended by AI kind of thing, such kind of indication is given in the report or not?
Yes, so we do mention that this is a computer generated. So we have a disclaimers for the legal purpose as well. So we do mention that whatever report is being generated is computer generated, and we have. That's why if you see the flow, we have a human in the loop also, the doctor. So basically, for those cases where the doctor is certified, the doctor is more liable. Or if the doctor is not certified, we will say it's a computer generated report. It has to be taken to a doctor for the proper interpretation.
Okay.
Hope that answered the question.
Yeah. Thank you.
Thank you.
Okay, sir. Thank you
Is
so
it
much.
is that a mandatory requirement from regulator or that you are giving actually?
So, good question. So I think it's the disclaimer is mandatory as per the standards, but I'm not sure whether the Indian regulator it is mandatory or not. But I'm pretty sure it is mandated by FDA. I have to check whether it is mandated by Indian regulatory clearances.
Okay. Okay. Thank you. Hope you're okay if I connect offline.
Yeah, definitely. Yes. So here is my email ID. So you can contact me.
Okay. Thank you. Thank you very much for the session.
Thank you.
Okay, thank you, sir, for your session. It was actually very informative, and we are really sorry for the disturbance that was happened between, and we truly appreciate your patience during that incident. And we would like to share a token of gratitude with this e-momento.
So, hello. Poonam is here. Will you please tell me about my problem? Dr. Shiva, are you getting me?
Yeah.
Poonamji, can you discuss later on offline?
It's okay.
Hi, thank
no
you.
issue, ma'am. Thank you.
Yeah, maybe Poonam, I think I have the email ID. Maybe you can get from the organizers also. You can contact me over email and we can have a Google Meet discussion. Yeah. Thank you for inviting me. It was a pleasure interacting with everyone.
Dr. Shiva, may I know where is your email ID? It's not showing
I will be
here.
sending in the chat, please.
Will you please text?
I will share you in person, Poonam madam. I will share you in person with you.
And one more thing, I would like to request all the participants to turn on your camera for the group photo. Okay, thank you, everybody.
Thank you, everyone.
Okay, so now I would like to invite our next speaker, Dr. Utpal Pandya. Utpal Pandya sir is a professor in the Department of Instrumentation and Control Engineering at SCAT, Surat. Sir has done MTech in Biomedical Engineering from IIT Bombay and PhD from IIT Bombay. Sir has more than 27 years of experience. Sir has received many research grants, including MODROP and Guj Coast. And today, sir is going to deliver a talk on Bluetooth ECG opportunities and challenges. I would like to welcome Utpal, sir. Thank you, sir.
Thank you. Thank you, Karisma. Am I audible?
Yes, sir, you are audible.
Should I start now or what?
Yes, sir, you can start.
So I hope the presentation is visible to everyone.
Yes, sir. Please make it to full screen.
Is it fine now?
Yes, sir.
So good evening, everyone. Today I am going to share my experience, what we have done to develop the hardware and the software part, and the challenges faced during that development process. So basically, my talk will focus on the capturing of ECG, its processing, and then transmitting in the wireless environment using Bluetooth. And when we receive the Bluetooth ECG at receiver end, you know, reconstruction is very important step. So what challenges we have faced during the receiving of this Bluetooth ECG, and how we have done the signal processing of that, so that the ECG can be cleaned and then further it can be used for the diagnosis purpose. So that is the objective of the today's presentation. And meanwhile, in the end, how Bluetooth can be used for many conditions to monitor not only one patient, but many patients. Not only one parameter of one patient, but many parameters of one patient as well as many parameters of many patients. So that we'll discuss in the end. So I hope it would be fine for everyone. So what we did, we have developed the front end for ECG. Then we interface that board with Bluetooth transceiver board. So on the receiving part, we have implemented algorithm. The algorithm which was used by the professional suppliers, as well as we try to identify their limitations, and then we develop our algorithm, and that is implemented. So results are discussed. Then the Bluetooth ECG for different activity of subject we have captured. So when it is called ambulatory ECG. So when the patient is moving and doing different kind of activity, what kind of how the heart behaves in that situation, that we try to capture and process and try to interpret. So you know why the body area network or wireless sensor network is required. Vital sign measurement. So there is a hospital scenario, no vacancy, high cost, risk of infection, lack of adaptation of environment, and lack of productivity. So this is the hospital scenario. When we talk about rural area, there is unavailability of diagnostic equipment, doctors, electricity, communication facilities. That's very much. Third situation is emergency medical care. So in the emergency medical care, you know, it will be ad hoc network. Emergency medical care, there will be ad hoc network. So
Patil, please mute yourself.
It is a different challenges compared to hardware or fixed network. Case of mass casualty events, this again represents a different scenario. So this is the requirement of body area network. Now, when we think about telemedicine system, then, you know, from doctor's point of view or from the designer point of view, you know, we need to provide two modes. One is normal mode That is, we'll call it store and forward. So, the data is captured, and once the data is captured in mobile device, then it can be forwarded on the request. Okay, so that is normal. Then real-time mode, when the doctor's request, okay, doctors will ask the patient to send the real-time data. So that is, real-time. So device which is designed must have both the capabilities. It should capture data in normal mode as well as the real time. Now, when the doctor receives the data at its end, then the doctor can instruct the patient to do certain tasks like change the sensor setup, give instruction. He can give the instruction to the patient, and then if the doctors found that there's an emergency need, then a patient is asked to contact the emergency department. So that is a requirement from the telemedicine side. Now, when we need to provide the real-time mode, the real-time mode depends on the parameter being measured. We have actually in the vital signs, we have blood pressure, ECG, body temperature, oxygen, saturation of oxygen. These are the parameters considered as vital sign. Now, if you look at the sampling rate requirement, blood pressure, if it is measured once in a minute, it will be sufficient. And resolution requirement 16 bit. So if we consider the required throughput, so it would be around 0.3 bit per second. For ECG, in 1 second, there will be 200 samples requirement. And at least 8-bit ADC is required, or 8-bit resolution is required. It is for monitoring grade. But if we want to design a diagnostic grade equipment, then 16-bit requirement is the minimum. So if we consider 8-bit, then the throughput will be 4800 bits per second. And valid ECG, again 200 samples per second is the requirement, sampling rate. And if 8-bit is considered, then the throughput requirement is 19,200. So here the point is, when the instrument is operated in real-time mode, it requires a lot of memory space as well as it consumes a lot of power. So when we design an algorithm, we need to design an algorithm in a way that the memory requirement is optimized as well as the power consumed by the algorithm should be minimized. So that is one requirement, that is a challenge. So this is telemedicine. And now when we move towards the WSN requirement, that is wireless sensor network or body area network, then
sorry to interrupt.
Yes.
Yeah, could you please go back to previous slide? I'm sorry, actually, see one clarification.
Mhm.
So here ECG you mentioned is how many leads?
ECG, this is for single lead. The second one is. Okay, and
single
third
lead.
third one is 12 lead.
So 12 lead ECG, that what you mean? It is clinically available in the hospital, and the whatever ECG mentioned in the middle, that is what you developed, something like that, right?
Yeah. And in fact, in the wireless devices will have always a single lead ECG.
Okay.
Because the reason is, you'll come to know why the reason is, because the reason is the throughput. Okay. So in the single lead, long-term patient monitoring, you require single lead ECG, not 12 lead, because 12 lead to carry is very difficult for the patient for longer time.
Okay.
So here the second row is for single lead ECG. Fine.
Okay. Is it something like that? Electrode also designed by your team, developed by your team?
Electrode is not designed. Electrodes are readily available in the market, and that we have
thank you.
silver chloride electrode is used. EGCl2 electrode.
Yeah, sorry to interrupt you. So continue.
No, please. WSN requirement, ad hoc deployment will be required in medical emergency. Then, when we go for that, then wearable platform is a challenge. So wearable platform, when we talk about, then small, lightweight, and wearable is the design criteria. Then second one is the reliable communication. So there will be temporary packet loss and persistent packet loss. So, when there's a persistent packet loss, then problem, it is not accepted. The reason is, the sampling rate at 100, minimum sampling rate requirement is 100 hertz to 1000 hertz. Okay. So when we go for higher sampling, it puts heavy demand on the communication channel. So that is a real challenge in real-time reliable communication. Then multiple receiver. There may be many cases like in the emergency situation, the data will be received by multiple doctors as well as nurses. So how we can establish that kind of network? And device mobility. Patients are also moving, caregivers are also moving. So, to keep the network intact by some way is again a challenge. And security, yes, the people are working on, to safeguard the patient data, to provide the safeguard the patient data, private key and the public key cryptography is used. And of course, the cost, to lower the cost, it is recommended that we should have modular packet. So actually, the rate fund, we have tried to address in our designing somewhat, not exactly everyone, but we try to develop to meet all these requirements. Wearable platform, so we have tried to develop the device small in size. We try to provide the reliable communication channel, then multiple receivers we have tried, and of course device mobility. With that, we have tried how much distance between patient and caregiver is allowable. Okay. Security we have not tried. Cost, of course, we'll discuss. So, and then we have started to see the literature, what literature says. So we found some interesting fact. Many researchers are trying for single parameter, and they have developed something using that prototype, that they have developed prototype using for only one parameter. Okay. Then they tried the filter algorithm, various filter algorithm, and mostly they are using MIT BS database. And in the MIT BS database, earlier there was no wireless ECG data. So it was very difficult to, now the algorithm was developed for the wired kind of thing. And if you want to implement the ECG on the wireless ECG, then there was a challenge. So something, that part we try to address. Then, of course, there will be motion artifact, and motion artifact means when we try to capture the ECG, the respiration rate or the movement of muscles is going to add the noise in the ECG. So we need to filter out that motion artifact. So it is still the motion artifact, removal of motion artifact is a big challenge. And there is a requirement of algorithm to prevent loss of clinically significant data. So when we reconstruct the signal, there should not be any loss of clinical data. That is a challenge. So actually, this is the architecture, and we tried to address the first one. So we have captured the ECG, then interface with the Bluetooth. So this was not in our scope. We have tried to this, the circle part, that part of architecture we tried to. Now the design challenges. So it depends on the type of transmitted data, vital signs, audio, and images. What kind of data we want to transfer. So there are, in the vital signs, we have bioelectric variables like ECG, EMG, EEG. Physiological variables, we have blood pressure, blood flow, temperature, and oxygen concentration. We are not going to discuss about colors and monochromatic and moving and stuff. There are many options in the wireless technology. We decided to go with Bluetooth because Bluetooth is available in every mobile devices, every laptop, and so all the most of the mobile device you will find the Bluetooth chip. So we decided to go with Bluetooth. Wi-Fi, why we have not gone? Because the Wi-Fi require lots of power. So, power consumption will be more in that. So we have selected Bluetooth as a wireless technology. What we found in the Bluetooth enabled device. So developers have developed their Bluetooth device for single parameter. So if they have developed that device for blood oximeter, that device will only useful for the blood oximeter. So there is no flexibility. Second thing, the flexibility in case of Bluetooth transceiver. Once the Bluetooth transceiver is configured for one parameter, say for ECG, then that Bluetooth transceiver is only used for the ECG, cannot be used for another parameter. So what the outcome of it is that the hardware cost is increased. So if I want to monitor 4 vital signs, I need 4 different setups. I need the front end plus Bluetooth for each parameter. So total I will have 4 transceiver and 4 signal processing for 4 different parameters. Okay. So ultimately it will increase the system cost. And transmission range, most of the Bluetooth device that was reported in the literature, they have used the class 2 Bluetooth chip. So class 2 is actually permitting only 10 meters communication. But if we use class 1, then it is possible to communicate wirelessly up to 100 meters. And most of they have used the proprietary software. So that is the issue with the earlier development. Now, so we try to develop our hardware. So we found 3 different options how we can develop the hardware part. So we can have analog front end here, which will have the amplifier plus filter. Then we can have ADC plus microcontroller, and then Bluetooth transceiver. So this is option 1. Now we have second option, system on chip. Now in the system on chip, we can have amplifier, filter, ADC, and microcontroller. And we can interface it with the Bluetooth transceiver. The third option is we can develop analog front end, and then we can interface this analog front end with the system on chip, which has the ADC, microcontroller, and Bluetooth transceiver. So depends on the your project length, people involved. You can adopt any of this, but we have adopted the third option, that is analog front end we have developed, and the system on chip, which has on the chip we have ADC, microcontroller, and Bluetooth transceiver. So this option we have selected. Now the ECG part. So actually there are 8 to 10 attributes which are looked by the doctors. Like there are segments, there are intervals, the amplitude of different waves are looked by the doctors to diagnose the various disease condition of heart. Like if you want to tachycardia, bradycardia, or myocardial infection, any disease condition can be estimated using the 8 to 10 parameters of this ECG. So this is actually the standard ECG waveform, and the literature shows these are the standard frequency, or you can say the time interval of different ECG waveform. So ECG is comprising of P wave, QRS complex, and T wave. And sometimes the U wave is also seen. QRS complex, 90 millisecond is the standard time. Means if it is normal, then the length of this QRS complex would be around 90 millisecond. PR interval, so it is starting of the P wave and the starting of QRS complex is called PR interval. So it would be around 150 to 200 millisecond. So we'll find this kind of data in literature. So this is a standard ECG pattern. And in fact, and this is the recording chart used by the doctors to print the by the doctors. So this is, we have developed lead 1 ECG. So it is between RA and LA, right arm and LA, left arm. So 2 electrodes are placed on the right arm side, and one electrode is an RA part, and another is the left arm, and right leg is used for the feedback. And this is a circuitry schematic of our design. So we have used INA 326 from Texas Instrument, OPA 2335. It's an operation amplifier. INA 326 is the instrumentation amplifier, and use the high pass filter, low pass filter. And so that way we have designed. So this is the schematic of front end. I'm not going more in detail into this, how we have removed the electrode offset potential method. You can see here the 3 boards. The first one, that was the try 1. With the same schematic, we have tried to, develop this board. Then second, because this board could not work, so we try to change the size of the board, but still it could not work. And the third design, that design has worked. Same schematic, when we design the PCB, there will be, mutual capacitance or inductance between the track. So we need to design very proper, all the tracks should be designed properly. So surprisingly, the third board has worked, and the size of that prototype ECG board was 60 to 45 square size. So here we can see that board. So we need to be very careful about the size. If we try with the smaller size, but possible, it may not work. So this is a testing of the ECG board. On the DSO, we have tested the ECG board. Then the Bluetooth transceiver. The second part was the important hardware was the Bluetooth transceiver. So this is our model. Okay. So we need to integrate our Bluetooth ECG module, that is analog front end, the Bluetooth transceiver. It will send the data to the receiver. This is a serial port device, and here is it is connected with the laptop or computer. So we tested this Bluetooth transceiver, Bluetooth transceiver also using simulated function generator. So this function generator has provided the ECG signal. So we transmitted this simulated ECG signal through this, and we have captured that ECG at the receiver side. We varied the frequency, we have varied the amplitude, and we capture the ECG, and we assure that this board is perfectly suitable for the capturing of ECG. So this is the hardware. So here we have ECG board, the Bluetooth module, and the receiver side we can have serial adapter as shown in here, or we can have Bluetooth USB dongle. Any USB dongle can be used. And the software that we have used is Terraterm Pro to capture the serial data. Then Blue Soleil, this is to establish the link between 2 devices, the transmitter and receiver. And the data is captured in Excel as well as the MATLAB. So this is a screenshot. You can see the active devices over here. So this is actually Bluetooth transceiver is connected with the Bluetooth. Now, so when we have captured the data and in the sitting position, the subject was asked to sit in the chair, and we capture the data. We capture the data at the different frequency rate, like 100 Hertz, 150 Hertz, 200 Hertz. Actually, this Bluetooth board, Bluetooth transceiver, has the facility to select the different sampling rate. And it also has 4 channels. So if I want to connect 4 different board, I can connect. If I want to adjust the frequency, sampling frequency, I can do that. But there is a limitation. I can implement only 1 sampling frequency for each parameter. So I mean to say, if I connect the Bluetooth, say I connect the blood pressure parameter and I connect ECG. Now blood pressure requirement only 1 minute per second. One sample per minute is required, while ECG is required 200 samples per second. So in that case, I need to keep my sampling frequency around 500 Hertz. Okay. So although Bluetooth blood pressure has the requirement of 1 sample per minute, I have to use the 500 because there is no facility. For individual channel, we cannot select the individual sampling rate. So that is a limitation. So what we did, we captured the ECG at the different sampling rate. Now you can see, so there is, something, it is called baseline. So 100 Hertz, so each frequency we have seen the baseline. So this is for the different, again, different condition. It is the patient who was standing and we captured the ECG. Interestingly, you will see that the baseline frequency is little bit increasing when the patient moves from sitting to standing position. So baseline is the issue. So what we did, we need to remove the baseline before we process the ECG signal. Now, what we have implemented, we implemented a fast Fourier transform and IFFT algorithm to remove the baseline drift. So this was our first step. So we observed that around the baseline frequency is 0.15 to 0.5 Hertz. And in the ambulatory ECG, that means the moving ECG, moving patient ECG, it would be around 1 Hertz. And if we see the frequency of ECG signal, different ECG signal, then you can say that see that the QRS complex 111 Hertz, P wave has 8 Hertz, T wave. So simply what we did, we have removed the one. So we capture this in time domain. We have implemented FFT. So it converted, it is kind of frequency domain. In the frequency domain, we have just removed the 1 Hertz data, 1 Hertz frequency. Then again, we have implemented inverse FFT. So again, we converted that frequency domain signal to time domain frequency. So after that, we are able to remove the baseline drift. So now you can see here. So this is a captured ECG with the baseline drift. Now in the blue, red, and purple is showing the ECG without baseline drift. So 1 Hertz was cutoff frequency for baseline. So simply we have implemented FFT and IFFT. So this is for the higher frequency when the ECG is captured 500 Hertz. Now, so baseline is removed. Now, what about other noises? You can see this is not clean, right? So we need to remove this noise also. So what we did, we have referred the literature and we found that these 3 algorithms are widely used by the developers. Like one is the piecewise moving average. Now there's a moving average that is fixed point, and third one is the as-goal. Okay. So where in all these 3 algorithms, the parameters were fixed. Okay. Say as-goal, it's a polynomial base, and degree was 5 and frame size 50. So in one sample, it consider 15 RP, and then it will be implemented. So we implemented these 3 algorithms, and you can see here the results. So if you compare with the earlier one, say baseline corrected, you can see a lot of noise is removed. Still, we found some issues with these algorithms. So this is for the standing position. Then, one book was suggesting about the ensemble averaging. Can we implement ensemble averaging on the ECG or not? So we studied the manually at the back. We want to identify the fiducial point on the ECG. Fiducial point means it's the one point where everything will get repeated. So we try to identify that location. So we manually try to find out the R peak location where R peak is occurring. So this is the data for different kind of ECG. So what we found, if you can see here, the fiducial point, the first condition for ensemble averaging is the fiducial point should be fixed. It should be repeated at the same sample number. So you can say it is not remaining constant, it is changing. So when we implement it, ensemble averaging, it is not giving us the result. So here is a limitation what we have seen. Piecewise moving average, limitation is high frequency noise is not removed. If we implement fixed point moving average, sharp variation average out and attenuation of amplitude. So certain diseases are identified the amplitude of the ECG signal, R wave. So it is getting attenuated. So this is not accepted. With the fixed point, high frequency noise is not removed. And as Gole, no effectively reduce low frequency noise. So here the need of the algorithm which can address the limitations of all above three algorithms. Then when we once we know that these are the limitation of already existing algorithm, actually these algorithms were implemented in the ECG when captured in the wired condition, not on the wireless data. Now when we have tried this, parallelly we have observed these two issues: data latency and so when so fidelity and data latency, these two issues we have seen. So when the battery power goes to certain level, the specified distance increase between patient and the caregiver, there is a data drop. So here you can see actually the Bluetooth transceiver send us the standard is 4 hexadecimal value is sent by the Bluetooth transceiver. But when this occur, the battery power level goes. So sometimes it will send the 6 hexadecimal value, or sometimes it may send 3 hexadecimal values or 5 hexadecimal values. So when we convert this hexadecimal value in decimal, this is the voltage. Actually, this is the formula that we have used. It is 16-bit ADC. So we have used this formula. So when we convert, actually the signal level should be between 0 to 5 volt. But when we receive 6 hexadecimal value, it is 90.426 voltage. Okay. So it is due to data latency and fidelity. So this is again now one more challenge happened in the wireless scenario. So when we plotted the ECG, we were surprised nothing is seen, because actually happening with this. So when we receive the 6 hexa value, nothing can be seen. So if we remove this, then definitely we will be able to see the ECG. The another issue is, see, most of the device, the wireless device, allowed the over the air operations. Okay. Over the air operation means you can configure your Bluetooth transceiver remotely. So when we configure the device remotely, then data type is getting changed. So like here, this Bluetooth transceiver is sending this kind of data. Configure it over there. Right? So once it is configured, again it will start sending the 4 hexadecimal values. So we'll be able to convert. So when we operate the device over the air, then you can see this silent zone, because this data type is different. It is just like this. Okay. So, when we plot this silent zone, and then, suddenly once the configuration get over, you will be able to see this ECG. So actually this is not acceptable in wireless devices. It should be some way, somehow we need to remove it. I hope this is okay for everyone. You might have, implemented part of it, or you might be knowing, or you might have implemented more than this. If it is so, please share your input with me. In fact, we try to capture the ECG. We developed the template in Excel, and we try to capture the ECG in the real-time mode, and we were able to plot the ECG in Excel also. But the fast Fourier transform and other thing was not possible with this template. So baseline removal was not possible. So algorithm implementation summary is possible to capture real-time ECG using hardware plus MS Excel, discussed here with a certain limitation. And null algorithm is required. So should be able to remove low as well as high frequency components without attenuation of signal. And that should work for any sampling rate. And should be able to handle the issue of wireless fidelity and latencies. So this was the requirement for the null algorithm. So we have proposed this algorithm, Plasma algorithm. It is called peak rejection adaptive sampling modified moving average. In fact, you will find one IEEE transaction paper on this algorithm. So again, the ECG, just to remind you, it has certain fixed parameters. Now, what we did in our algorithm, we have divided the ECG in the three segments. First is the initial part, second one is the mid part, and third one is the final part of the ECG. So mid part, if you see, it's at high frequency. QRS sample, QRS interval has the highest frequency. So idea is, let us do not implement any filtering on the QRS complex because there is very less possibility that the QRS wave is getting corrupted. So there is very much possibility that your P wave and the T and U wave may get corrupted. So what we did, except QRX complex, let us implement the filtering algorithm on S-in and S-fin segment. So that was the idea in this part. Well, there are interesting issues we have faced. When we start capturing, okay, let me go through so this is the mathematical representation. So smoothing factor, because we have implemented here moving average and the first part and the last part we implemented moving average and except QRX complex. And the smoothing factor, what we did, we have kept it dynamic. So we need to select the sampling frequency, and based on the sampling frequency, the smoothing factor is getting selected. Same way the QRX complex, so size of QRX complex. So number of sample size will increase as we increase the sampling frequency for QRX complex. So again, what we did, we have connected it with the sampling frequency. So QRX complex sample will be, number of samples will be sampling frequency divided by 50. And interval, that would be sampling frequency divided by 1.6. So this parameter we have kept dynamic in our algorithm. We have seen some good result also. So now what happens when we implement the moving average in initial and last phase? So, in the initial phase, so we have only say, for example, the 4 samples I am considering as a moving for the filtering. So when I capture the first sample, it would divide by 4. When I capture the 2 samples, 2 divided by 4. Okay, the 2 values of sample divided by 4. So initially, at the initial point, we'll be able to see this kind of thing. Same way, if at the final age, same final point or final sample, this is also occurring. Like if say n number is the final sample, total number of samples. So n minus 4, it will be divided by 4. N minus 3 sample number will be divided by again 4. So it is not remaining 9. So in the starting phase and the final phase, there was a problem. So we also removed that. So this is, the flow chart of the algorithm, Plasma algorithm. So enter sample range, enter sampling frequency. Sample range for what? Say there are 10,000 samples you have captured. So up to what sample numbers you want to, how many samples you want to consider. for the filter. Say 1 to 5,000, 1 to 8,000. So that we need to select. And enter sampling frequency. So from that, it will calculate all other parameters. So next step, import text file of receipt ECG via Bluetooth link. So we have used Teraterm, it's a freeware. So Teraterm is capturing data in the text format. It will be hexadecimal. So we need to convert into decimal values. Okay. Now check bit length of each sample. So as I said in the initial samples, like sample number 1, sample number 2 and 3, they are getting divided by 4. So what we did simply, we have discarded that samples. Okay. So once we were considering 4 samples only, not 1, 2 and 3. So 4 samples we divide. So that will give me the correct value. Okay. Then remove baseline drift. Then to determine the RR frame length. So first 6 R peaks are considered and find out the average of RR. Okay, we'll share the PPT, and if you are interested, I will share the code also so that you can do further exercise on it. You can do further development. Okay. So apply modify moving average on the sample values except QRX complex. So now let me show you the result. Okay. So you will see the result visually, how you will be able to visualize that, okay, the plasma is working good compared to all other algorithms. And second mean to estimate the algorithm, we tried the quantitative analysis. So we have adopted 2 performance indexes. One is root mean square deviation and second is the signal to signal plus noise ratio. So actually why RMSD, this statistical parameter is selected to compare the performance algorithm, because when you have 2 signals, both are not standard, then the RMSD statistical parameter is used. Okay. So RMSD is used to compare difference between 2 things that may vary, neither of which is accepted as a standard. And so here ECG capture is the arrow of ECG captured wirelessly via Bluetooth link. ECG filter is the arrow filter ECG, and e-signal is the filter. So this is, how it is implemented. Simple formula. See, we have not used the code, ready-made code available in the MATLAB. We have designed, we have written loop ourselves. And another parameter that we have used is signal to signal plus noise ratio. So this is the formula we have implemented. So the visual representation of captured ECG. So first is captured ECG. So this is for all the at the different frequency. So earlier it was the sitting position. This is the standing position. Then the captured ECG. And the B, that is the baseline corrected ECG and plasma. So you can see the blue one is the plasma algorithm implemented on baseline corrected ECG. Now plasma is compared with the moving average filter. So blue one is, see here when the moving average is missing this means this ECG, that is also captured by plasma. Okay. So you can see less attenuation in the S-Gole also. So this is for 100 Hz. So same way we have implemented plasma algorithm and compared at the 250 Hz, same way 500 Hz, the different position. For different region, we tried to work out the RMSD, root mean square deviation, and except one point, when RMSD is low for one algorithm, that means it is removing higher noise. Okay. So you can see that except one case, the RMSD values are lower compared to moving average and S-Bullet. Same way, the SSNR higher value, that means it is removing more noise. So both the statistical parameter is showing that the plasma algorithm is working better than MA4 and S-Bullet. So this is just, we have discussed what are the plasma features. Of course, there are certain limitations of plasma. One can work on it. The RPIC determination is based on frame size. So right now we have considered first 6 RPIC. So then only we are considering at what number of samples RPIC is occurring. And the constant RC determined by the statistical analysis. For another parameters like EMG, if we want to implement plasma for different other bioelectric signal, then we need to work out for RC parameter. So that is a challenge. So plasma algorithm, you can see it is again the ECG. But if you want to implement for EMG, EEG, we can definitely go for it, but we need to work out RNC parameters. So, we have tested in our lab with the different students in different conditions, patient condition. Then we move to hospital to validate our device, our prototype device. So we have simultaneously captured the data with our prototype device as well as the device used by the doctors. Okay. So one is the TMT test, treadmill test. So we're able to find almost, with good accuracy. It was very much comparable with so earlier it was with the TMT. Now this is for, the recorded ECG. So this one ECG, lead one ECG, and we have compared. So we have validated our prototype in the hospital. So this is a TMT test, and this is a result of our algorithm. You can see again the plasma is doing that. The algorithm TMT also. Treadmill is a certain protocol. So like there are different stages. For different stages, the ECG is captured. Like stage 1, the speed of the treadmill will be around 1.7 mile per hour. Stage 2, it will be 2.5. So speed is increasing at the same time, the inclination angle will change. So in the TMT also, it has worked somewhat, but still more experimental work is experimental validation is required. And we use our prototype device to capture the ECG at the 100 Hz frequency with, when the person is driving the vehicle. Of course, we need to keep our receiver in the range of that driver, right? And, when the person is playing a tennis, so the person is wearing the prototype device and captured that also. So actually, when the person is moving, there is a lot of motion artifact that will introduce baseline drift, and the filtering, and that is a big challenge. So that was for, single patient, one ECG sent by the patient and the received by the Bluetooth. Then, we try to implement Piconet. In the Bluetooth Piconet, we can connect 7 Bluetooth transceiver, and there will be 1 receiver. So we use 2 prototype modules, and connected with the laptop. So you can say there are 2 patients, and we are monitoring ECG of both the patients. So walking, jogging, again playing any staircase climbing, this experiment. No, you can see in the two active modules, Bluetooth transceivers. Subject 1 ECG, subject 2 ECG. Now what we have learned here, that you can see that the peak value is different. And the walking, jogging, okay, playing tennis. So observation is compared the performance of. So here the discussion point was, at the beginning of experiment, the battery level of subject 1 device was 5.8 volt DC, while for subject 2 it was 6. So R wave peak of the subject 1 is less than subject 2. Obviously, the 5.8 volt is supply, right? So peak was little bit less than the subject 2. Then, the length of cable, ECG cable, was not same. So that has also introduced the baseline drift and noise due to cable movement with varying nature in different conditions like standing, walking, staircase, and climbing. So again, in this scenario also, the Plasma algorithm has worked very well. It has provided less attenuation compared to other.
So what is the type of battery used actually? Is it a coin cell kind of?
Lithium-ion battery, sir.
What is
5.5
it?
lithium-ion battery, 5.5 volt.
Okay.
Rechargeable. Okay. Then, in the simulated we tried this different scenario. Point-to-point to multi-channel sensor. Point-to-point multi-channel. I mean to say, as I said, on the Bluetooth transceiver, there were 4 channels. So can we connect 4 different type of parameters or not? So, we have considered ECG, blood pressure, SpO2, and body temperature. So you tested this prototype board in the simulation. So we have used the source, which can produce ECG, which can produce blood pressure, SpO2, and body temperature. So source is producing equivalent signals in voltage. So we have connected with one board 4 parameters and receive the data. Then multi-point to point. That means more than one patient. So we have tried 7. We have 4 prototype devices. So we have connected 4 prototype devices with a single receiver. As I said, in emergency condition and the wireless sensor network requirement will be different. Okay, there may be possible that many patients require to be observed simultaneously. And, one data is also required to be sent to many people like nurses and doctors. Okay. And the third option was multi-point, multi-channel. So it was expansion of multi-vital signs of more than one patient. Just will show you. This is what I said. So 2 channel is used and it is tested. So this is actually the actual wave sent. These waves produced by the source function generators, programmable function generators. Then it is given to the our prototype board. So this kind of data is reproduced. And this is a scenario. So earlier we implemented for 2 subjects. So in fact, 7 patients can be monitored using one Bluetooth receiver. We have implemented it for 2 patients, like one patient 2 parameters, another patient again 2 parameters. So again, the one patient on the one channel we have sine wave. So all this, once, your board start working, you would like to try it for different conditions. So we have captured it on the mobile also. In fact, in the one of the MS Microsoft mobile PDA device, it has the small version of Excel. So we were able to capture capture with the reproduce the ECG with the MS Excel also. So this is a conclusion of the, actually, this is, body area network. So when we move from wireless sensor network to body area network, again, there is a challenge. Now, what we see right now, if you go to the hospital in ICU or semi-special room, each patient is wrapped up with the cables. So they have vital signs connected with the ECG monitor, the multi-channel monitors. So there's a cable. So, it restricts the patient movement. So if we implement using this kind of prototype board, or we develop the system, then it is possible to have the ICU scenario like this. You and the patient have wireless sensors, and there is no connection between the patient and the monitor. Okay. So all the data is sent to the monitor using wireless channel. No, there is no need of cable. So such 7 patient beds can be connected, so total you can say 28 parameters of 7 patient can be seen on monitoring table. Same way in the semi-spatial room, if you go, we can implement, we can design the network like this. Again, there will be, wireless sensors for patient, and this can be. So this is what multi-channel, multi-point, multi-channel possibility. If you talk about the system cost, almost constant for any application, only we need to change the front end. See, it is a modular approach we have adopted. So front end plus transceiver. So there is a high cost of course, there is a high cost of Bluetooth transceiver, but the development process will be a very low, very fast and very low. One person can easily develop the device for any parameter. So if I want to monitor respiratory rate, what I need to change, I need to change the front end. The remaining part is tested and validated. The Bluetooth transceiver part is tested and validated. So just I need to validate the front end of the respirator. So, so development is very fast with such kind of approach. Receiver hardware cost is almost nil as it is Bluetooth enabled. So if we add more channels, that Bluetooth transceiver cost can be justified. So actually when we have tried to develop, so this was the cost estimated. In fact, actually I worked with Professor V. Desai of IIT Bombay earlier, and he was with the IIT Hyderabad. So we have jointly worked on this under his guidance. We have worked on this device. So these are references I have used. The reference. So thank you very much, and let me have your questions if you have any.
Sir, what is the Bluetooth controller part name?
Bluetooth controller. I'm not getting
Yeah,
your
so
question.
the chipset you have used, right?
Yeah. So it has, can you able to see the PPT? So, this Bluetooth part, actually, that I'm saying that it is from Roving Network company. Okay. So that this is the third option, right? It has system on chip. So that Bluetooth transceiver consists of A to D converter, microcontroller, and Bluetooth receiver. So this is the
Okay.
system on chip. So actually the advantage is, if you're a little bit knowing about the how to interface microcontroller with the Bluetooth receiver, you don't have to worry. Okay. Same way, if you don't know how to interface ADC with microcontroller, it will be taken care. Somewhat flexibility, like in the first option, this is the first option is complete flexible. You have front end different, you have developed, you have ADC and microcontroller, you have separate one. Bluetooth transceiver is also, you have separate one. This is a complete flexible approach. But then you should have the knowledge of, the interfacing of microcontroller with the Bluetooth transceiver, as well as interfacing of front end with the ADC. If you are not comfortable with this or this, you can go for the option C. So, I mean to say, if you want to develop hardware or software, or you want to combine both the things. So in our case, we have seen that there's a possibility of development of algorithm on wireless data. So we want to move in that direction. Now, what happened when we refer the MITBS database, we could not find the wireless database. So of course we don't have, at that time we don't have the choice. So we need to create our hardware so that we can capture the wireless data, and then we can implement the algorithm. So that's why we have adopted the third one, third option.
Okay, sir.
Anyone? I was a little bit fast. I have not discussed about the removal of noise part because, then I have to skip the software part. So I have not touched upon that part.
Sir, one last clarification. When this work is carried out, is it a recent work or a few years back?
You can say it is 3 years back because, we are constantly upgrading it. When it is not in the market, but we are upgrading it. Say right, right now we have the enclosure was earlier with the, the square box. Now with the 3D printing, we have changed the enclosure. It is like in the heart shape. So exactly you can put that heart shape enclosure in your pocket. So it is like, external heart instead of internal heart.
Okay, sir.
Thank you, sir, for such an insightful session. And I'm sure everyone has gained a lot from the session. Please stop sharing the screen so that I can share my screen.
Just a minute.
Okay, sir. So thank you so much. So I would like to thank you on each and everyone participant. And I would request all the participants to turn on the camera for the group photo.
So you may connect on my email if you wish.
Okay, thank you, sir. And thank you, everyone. So tomorrow you are supposed to join at 6 p.m. and the WebEx link is already shared with you. So you can join at 6 p.m. tomorrow. Thank you.
Okay, thank you for inviting.
Thank you. Bye. Good night.
Thank you, sir.
Okay, thank you.